Hello everyone, today we're going to be doing problem 1.4 in Griffiths Intro to Quantum Mechanics 3rd edition. In this problem we have a wave function, which is this piecewise function here. It takes on this value from 0 to a, and then this value right here from a to b. So part A asks us to normalize it, which means just to find this constant a right here. So to do that, we invoke this property right here, which says that if we integrate the probability density over all space, or the wave function squared over all space, we are bound to find the particle somewhere, given that it's normalizable. So we can use this property right here to find A. So let's just go ahead and plug in our wave function squared. So from 0 to A, because from 0 to negative infinity, the wave function is 0. It's really just 0 everywhere except for these two regions right here from 0 to b. From 0 to a, though, we have a squared over a squared times x squared dx. And then we have an integral from a to b of a squared over b minus a squared times b minus x squared dx. So we just have to solve this integral and we will find a. So the first integral, let's just do this real quick. A squared over a squared times x cubed over 3 evaluated from 0 to a, plus a squared over b minus a squared. And then let's just FOIL this out. We have the integral from a to b of b squared minus 2bx plus x squared dx. In this first integral, you're going to need an a cubed over 3, and the a cubed will cancel with the a squared in the denominator. So you're just left with a squared a over 3 plus a squared over b minus a squared times, there's going to be 3 integrals here. The first one being b squared times the integral from a to b of dx, minus 2b times the integral from a to b of x dx, plus the integral from a to b of x squared dx. Okay, so we have a squared a over 3 plus a squared over b minus a squared times this integral right here is just going to give x, so it's just going to become b squared times b minus a. And then the second integral is just going to give x squared over 2, so it's just going to be b squared minus a squared over 2, which cancels with the 2 in the numerator. And then this last term is just going to give b cubed minus a cubed over 3. And now let's just go ahead and expand this right term right here. So we have a squared a over 3 plus a squared over b minus a squared. And then we have a b cubed minus a b squared minus b cubed plus a squared b plus b cubed minus a cubed over 3. And we see that this is almost resembling a b minus a cubed polynomial. But we need to multiply this whole thing by 3 so that we can get 3's in the middle terms, in the cross terms. And we also realize that these two cancel. So this is going to be a squared a over 3 plus a squared over b minus a squared. And then let's go ahead and multiply this by 3. To do that, we need to divide by 3 as well. And we're going to get b cubed plus a squared b minus ab squared minus a cubed. Sorry, there should be 3's here. And this term right here is just b minus a cubed. So that term is b minus a cubed, which will cancel with b minus a squared in the denominator. So we are going to be left with a squared a over 3 plus a squared b minus a over 3. And we can just go ahead and add these since they share a common denominator already. So this is equal to, you see that there's going to be an a squared b and an a squared a term, and the a squared a is going to cancel with this a squared a term, so you're just going to be left with a squared b over 3, which has to equal 1 due to the normalization property. So you just find that a is equal to square root of b over 3. So let me go ahead and box that, and that's the answer to part A. And part B asks us to sketch the wave function. So let's go ahead and do that. Here's our x-axis. And here's psi of x 0. Okay, so from when x equals 0, the wave function equals 0, and when x equals a, the wave function equals this root b over 3. And we see that the wave function is linearly increasing from 0 to a. So it's going to look something like this from 0 to a, where it hits a maximum at x equals a. And then from a to b, it's going to be linearly decreasing, but at a slower rate, because you have this b minus a term that you're dividing by. So it's going to look linear, but just with a slightly less steep slope. Sorry, let me just fix this a little bit. It's going to end up right here at b. So this is kind of like a triangle wave function, but that's what the initial wave function looks like. And then part C asks us, where is the particle most likely to be found at time equals 0? Well, at time equals 0, this is the wave function right here. So you can see that the particle, the value of the wave function is at x equals a. The maximum value of the wave function is at x equals a. So that's where it's most likely to be found at time equals 0. So at x equals a, go ahead and box that right there. And then part D asks us, what is the probability of finding the particle to the left of a? Check your result in the limiting cases b equals a and b equals 2a. So we know that the probability from a to b, for example, is given by the integral from a to b of the wave function squared dx. So this is the probability from a to b, and we're trying to find the probability to the left of a. So we know that from the left of 0 and on, the wave function is 0, so we just care about from 0 to a. And from 0 to a, the wave function takes on the value of the normalization coefficient a times x over a. So when you square that, you just get a squared over a squared times x squared dx. So this will be the probability to the left of a. And now we just need to solve this integral. A squared is 3 over b, so this becomes 3 over a squared b, and then times x cubed over 3, evaluated from 0 to a. And the 3's cancel, and we're just left with a cubed over a squared, which just leaves a over b. So this is equal to the probability of finding the particle to the left of x equals a. And we want to check the limiting cases to when b equals a and b equals 2a. So first with b equals a, you just see that a over a is 1, so the probability is guaranteed to be found to the left of a. So probability equals 1. And then when b equals 2a, we see that it just becomes a over 2a, which is 1/2. So the probability is equally likely to be found to the left of a and to the right of a. So that's part D. And part E is kind of long, so I will do that in a separate video.